All right, folks, we conclude Chapter 7 with a look at hyperbolic functions in Section 7.7. All right, when I took calculus, many, many years ago, this section, it was an entire chapter. There was an entire chapter dedicated to hyperbolic functions. So here we are now. Instead of an entire chapter, it's just simply one section. And this is mainly because the importance of hyperbolic functions has been diminished, in particular in the construction world. They were starting to become diminished when I was learning calculus, but because of breakthroughs in material sciences, hyperbolic functions no longer had to be used in the construction of certain objects. And as a result, they've really lost their importance. So we don't spend a chapter on it anymore. We simply spend a section on it. So with that said, this is going to be a brief overview of these functions. I will stress and let you know the definitions I want you to know. I'll also stress any derivations that you should be able to do as well. So here we go. Let's talk about these hyperbolic functions. Now we know trigonometry is based on the unit circle. The hyperbolic functions are based on something called the unit hyperbola. And there's the graph of the unit hyperbola. And here's how the hyperbolic functions are defined. All right, take them one at a time. SINH, okay, I'm just going to call that hyperbolic sine. So hyperbolic sine of x is defined to be e to the x minus e to the negative x over 2. Likewise, hyperbolic cosine of x is defined to be e to the x plus e to the negative x over 2. Notice hyperbolic tangent is hyperbolic sine over hyperbolic cosine. That kind of reminds me of trig. Notice that hyperbolic cosecant is the reciprocal of hyperbolic sine. Notice hyperbolic secant is the reciprocal of hyperbolic cosine. And notice that hyperbolic cotangent is hyperbolic cosine over hyperbolic sine, or the reciprocal of hyperbolic tangent. So there's kind of a connection to trig as well. It looks like there's some identities that we know from trig that appear to be true here in the hyperbolic world. So here's what I would say definition-wise. I would like you to know the definition of hyperbolic sine, and I would like you to know the definition of hyperbolic cosine. Then everything else here is free. The hyperbolic tangent, knowing that it's hyperbolic sine over hyperbolic cosine, that is free. As is hyperbolic cosecant, hyperbolic secant, and hyperbolic cotangent. So make sure you know the definition of hyperbolic sine and hyperbolic cosine. There are many identities in the hyperbolic world, and some of them are shown on page 501. What I thought we would do, let's head to the board and let's show how to verify an identity. I'm only going to do one of these, and it's the identity hyperbolic cosine squared x minus hyperbolic sine squared x equals 1. So this is an identity. We're just going to head off to the board real quick and verify this identity. All right, I said we'd head to the board to verify the identity hyperbolic cosine squared x minus hyperbolic sine squared x equals 1. Well, just like in verifying identities that were trig identities, you do all your work on one side of it and try to get it to match the other side. Well, here we know hyperbolic cosine, it's defined to be e to the x plus e to the negative x over 2. So that's hyperbolic cosine, and then it's going to be squared, minus hyperbolic sine is e to the x minus e to the negative x over 2. And that quantity is squared. So what we have left to do, I guess maybe we could just actually do this, square it. So when I take e to the x plus e to the negative x, and I square that, I get e to the 2x plus 2 plus e to the negative 2x. And that's over a 4, because 2 squared is 4, minus, when I take e to the x minus e to the negative x and I square that, I get e to the 2x minus 2 plus e to the negative 2x, and that's all over 4. Since we have a common denominator, we might as well make one fraction. So, better draw that vertical line down a little bit further. We'd have e to the 2x plus 2 plus e to the negative 2x. Now remember this minus, it's minus every term there. So it'd be minus e to the 2x minus a negative 2, so that's plus 2, minus an e to the negative 2x, all over 4. And we have some stuff cancel out. Let's see, we have an e to the 2x minus e to the 2x. We have an e to the negative 2x minus an e to the negative 2x. So all that's left in the numerator is 2 plus 2, which is 4. 4 over 4 is 1. That's the right side of the equation. We have verified this identity. I just wanted to verify one identity because it kind of reminds me of trig, and we see like a connection between the hyperbolic functions and the trig functions. But let's head back to the slides and see what's next with hyperbolics.
All right. Check out this example. For f of x equals hyperbolic sine x, we are going to determine f prime of x. And I am not going to use the definition of the derivative to do this. So when I head off to the board, make sure you have this written down, because when I head off to the board, the first thing I'm going to say is, how is hyperbolic sine defined? And we should be able to get the derivative from known derivative rules. So here we go to the board to work through this.
All right, for f of x equals hyperbolic sine x, we are going to determine the derivative. We are not going to use the definition of the derivative because we know hyperbolic sine is defined as e to the x minus e to the negative x over 2, or if you prefer, that's 1/2 times e to the x minus e to the negative x. And we know how to differentiate exponential functions. So we get the derivative to be 1/2. The derivative of e to the x is e to the x. The derivative of e to the negative x is e to the negative x times -1. Chain rule, derivative of the exponent. So that'd be minus a negative, which is plus, which is nothing more than the definition of hyperbolic cosine. So we've just determined a rule. We have just determined that the derivative of hyperbolic sine is hyperbolic cosine. So why don't we go back to the slides and see what's next.
All right, folks, on page 503, you're going to see a theorem. I believe it's theorem 7.15 for derivatives and integrals. Now, I really do expect that you could derive any derivative formula. I also expect that you remember the definition of hyperbolic sine and hyperbolic cosine. This example, we're just going to practice doing some derivatives and doing some integrals. So parts A, B, and C, write them down. We're going to practice doing some derivatives. And in parts D and E, write those down because we're going to practice doing some integrals. So let's head off to the chalkboard and let's do these 5 examples.
All right, in this example, we were just asked to do the following. There were 5 parts. Parts A, B, and C were derivatives, and parts D and E were integrals. So I just have A, B, and C up here. So let's do those first. Part A, differentiate with respect to x, natural log of hyperbolic cosine x. So we know the derivative of natural log. We know it's 1 over. So we start off, we have 1 over hyperbolic cosine x times, now we have to do the derivative of the inside, and the derivative of hyperbolic cosine is hyperbolic sine, which gives us the derivative hyperbolic sine over hyperbolic cosine, which you know we could simplify that down to hyperbolic tangent. You know what, right now I'd like you to pause the video and I'd like you to try parts B and C. And then once you've completed parts B and C, restart the video. I'll be here at the board. We'll work through it. Make sure you have a correct answer. All right, part B, you were asked to differentiate with respect to x. X hyperbolic sine x minus hyperbolic cosine x. And notice here, you're going to need the product rule. So here's what I get. The derivative of the first function is 1 times the second function plus the first function times the derivative of the second function, which is hyperbolic cosine, and then minus, okay, the derivative of hyperbolic cosine is hyperbolic sine, and this immediately simplifies down to just x hyperbolic cosine x. Not too bad. Part C, well, we know to d dx e to the hyperbolic sine x. We know the derivative of e to whatever starts off e to the hyperbolic sine. And then times, you know, the chain rule, we have to do the derivative of the exponent, which is just hyperbolic cosine. That wasn't too bad. So let me erase so I can get parts D and E up here. A couple of integrals. We have the integral hyperbolic cosine square root x over square root x dx. That's part D. And then part E is the integral hyperbolic secant squared of 2x minus 1 dx. All right, this looks like I'm going to have to use a U substitution. Maybe it doesn't follow any of my guidelines, but maybe it does if I consider square root x's to be like inside, if I were to make parentheses. And then in either event, I'm letting u equal the square root of x. Okay, du is, okay, derivative of square root x, that's x to the 1/2. The derivative is 1/2 x to the negative 1/2. That's 1 over 2 square root x, which that means 2 du is 1 over the square root x dx. So see how that helps me? Because I'm turning this into hyperbolic cosine of u, and then this 1 over square root x dx is 2 du. So I'm substituting 2 du in for 1 over square root x dx. Put the 2 out front. Antiderivative of hyperbolic cosine is hyperbolic sine. Resubstitute. And that's it. Part E. I would like you to pause the video and I'd like you to do part E. When you're done, restart the video. We'll be here to make sure you have the correct answer. All right, part E, I would start off by letting u equal 2x minus 1. Then du is a 2 dx, or 1/2 du is equal to dx. When I substitute in, I have hyperbolic secant squared u And dx is replaced with 1/2 du. Put the 1/2 out front. The antiderivative of hyperbolic secant squared is hyperbolic tangent. And we'll resubstitute. And that is it. So folks, at this point in time, we finished section 7.7. So you can go do the section 7.7 exercises, and thanks for watching.